Hello and welcome everyone for our webinar today on July 8th. We'll be getting started in just another minute or two here. I still have a couple people joining with us. I'm really excited for our presenter today, Eric. His name's going to say Will Higgins, but it's Eric who joined us to talk about some of the work they've been doing on covering lagoon digesters, both in Iowa and Missouri, and maybe a few other places around the U.S. as well. Definitely one of the leaders of the industry. And I know that one of our highly requested topics was to talk more about case studies and how our company's thinking about what makes a viable project. So really excited today to have Eric talk through some of what they've been doing and how they think about making some projects come together. So if you do have any questions for Eric as we go, feel free to type them in the chat. I can't promise we'll answer them right at the moment they're asked, but by the end of the session today, we'll take a moment to make sure we come back and talk to them. So I've had the opportunity to work with Eric for quite a while now and have been really excited by some of the work that they've been doing, making these systems a little more scalable and figuring out how to make projects work on farms that have been a little bit more challenging in the past to think about digester systems. So with that, I'll hand it over to Eric, and thanks for doing this for us.
Okay. All right. Well, hello, everyone. And let's see. Can you guys see my screen?
Not yet. There it's going.
Which
Yes, but I
screen?
have the wrong view. So if you click on that little display settings tab arrow there on the top, you should be able to flop the screen. Do you see that?
Uh, Hold on.
Share the other screen and it'll work out perfect.
Does it ask me to share which screen?
It does if you have multiple monitors. If you don't have multiple monitors, then you're fine. We were just seeing presenter view instead of the presentation view.
Okay, here we go. Is that better?
Perfect.
All right. Sorry about that, everybody. So just today's topic, I'm going to talk more specifically about swine lagoon anaerobic digestion and how Roeslein has approached this on several of our projects. So, as Dan said, as you have questions, please put them in the chat and we'll try to answer them probably at the end. But first I want to, I got to do a little bit of the sales pitch. Let's see, how's it get to the next screen? Hold on, got it. So a little bit about Roeslein. Roeslein has been started as a aluminum can manufacturing company. So we made aluminum can systems and equipment that make the aluminum cans, not actually operating the systems that when they're in service. And then we have a renewable energy division, which I'm part of. We have a traditional oil and gas division, which is servicing a lot of oil wells and gas wells in Western United States. And then we have industrial manufacturing where we're building equipment for other people. So that's our four divisions. And then these are some of our partners and customers that we work with. And you can see there are a lot of aluminum can type companies, but also some, I don't know why that's doing that, but some renewable energy type things like Iowa Select Farms and Moss Energy, Smithfield, Seaboard. So we've got quite a few different partners in the manure supply to our systems. So a little more background about Roeslein Alternative Engergy, which is the renewables division. It was founded back in 2012. It became and it was its own separate company. And then in 2024, it was merged into the rest of Roeslein and Associates as a division. Right now, we have built, own, and operate 27 different livestock and native grass project sites across the U.S. We've got sites in Arizona and Utah, all the way to West Virginia, and I'm not West Virginia, just Virginia and North Carolina. And of course, we have a couple in Iowa and several in Missouri and some Texas and Oklahoma. And then we also have built biogas upgraders for other owners and operators, and we just supply the upgrading equipment, or we build the whole project, like the lagoon digester, the piping that connects things, the interconnect, and we supply the entire package so that someone else can operate it from there on out. We are also a part of a third-part owner in what's called Monarch Bioenergy, and then our other owners are Smithfield Foods and a private equity firm called TPG. So we have roughly 18 projects through the Monarch Bioenergy consortium. And then just a little bit about scale. So we have currently operating 27 sites. We have one site that's as small as 60 scuff per minute, and which produces about 10,000 MMBTUs of RNG per year, or 10,000 decatherms. And then we have 12 sites that are kind of that mid-range, anywhere from 200 to 600 standard cubic feet per minute, and then another 14 sites that are larger. And as you can imagine, how have we evolved over time? We went after the larger sites because the economics worked better. They were easier sites to connect into the pipeline, and we had more gas to sell. So the economics were better. But as time has gone on, there's fewer and fewer of those opportunities out there. So we've had to scale back and try to approach smaller sites. And that's where these last 12 have probably been done in the last, I'll say, 2 or 3 years. And then the 60 scuff a minute site was put in here just in the last year. And we have some sites in North Carolina where we're going to have 16 different upgraders, and they're all very small, like 25 scuff a minute and up to 100 scuff a minute, all combined into a single interconnect with the pipeline. And so also in our history, we've done different technologies for upgrading biogas. We've started with pressure swing absorption, and we have 3 of those sites that have that technology. We have sort of focused on the membrane technology, and we actually have developed the membrane sizing and modeling, and developed our own in-house membrane solution. And then we have a couple of mean scrubbers that we did for a client, so we're familiar with that as well. And those are usually used for bigger biogas projects. A little bit about me. I've been in the business for now over 35 years in the energy sector as a chemical engineer. I worked in oil and gas for 17 years. I'm not sure why that moved. I worked in cellulosic ethanol for about 9 years, and then I've been with Roeslein for the past 10 years, primarily working on manure RNG projects. And as we move forward, we're going to be working in other feedstocks, I think, as we go forward. So, and at Roeslein, I've had a number of roles. We were a smaller company when I started, and you have to wear a lot of different hats. So I've been involved in scoping and defining projects from the start, and I still do a lot of that. I've been an engineering process lead to develop all the P&IDs and PFDs, control narratives. I've been involved in commissioning and startup sites, and now the operations team reports to me at Roeslein on the sites that we are operating with our folks. And then the other part that I've gotten involved with is credit generation, which is all the data associated with the molecules that are put in the pipeline that are part of a program. And I'll get to that a little bit later, part of several programs that we can get higher prices for the gas we're putting in the pipeline. I got my chemical engineering degree from Iowa State back in 1990. So we'll get into the topic now. So anaerobic digestion is the microbial breakdown of organic matter in the absence of oxygen, and it produces primarily methane and CO2. There's some other contaminants that are included in the biogas, such as H2S, and sometimes there's some small quantities, ppm level quantities of other, I'll say, bad acting chemicals, at least for membranes, that we will address as well in our upgrading system. The 3 primary things we look at when we're developing a project on anaerobic digestion is like the feedstock. We want to know, what kind of animal is making the manure, because we can go to some tables and figure out how much manure is going to be produced, what quality is that manure, and what's the animal population or density. So if we know the permitted spaces and know what type of animal, say it's a grow finish site in the swine business, we could understand that that's probably 75 or 80% on average loaded population. So Uh, and then another thing we would like to know is like how's the manure being handled at the site currently? And that can tell us about the quality of manure, like how concentrated it is, or say maybe the age of the manure. So does it sit underneath the barn for a period of time and digest outside of a digester before we actually get a chance to put it under a cover and collect the gas? The next temperature profile is the next sort of important topic, is where you're located in the country. If you're doing a lagoon digester, there we typically do not heat or mix those, and so you depend on Mother Nature to provide the energy to get the bugs warm enough so that they start digesting. And it's all solar energy, so it really depends on what the ambient temperature is in that part of the country that you're located. And we'll talk about the temperature profile here in another few slides, but that's another important factor in determining your gas production at what rate and how much gas you'll produce over a year. And then the last item is the hydraulic resonance time. And this is basically how long does the manure or the digestible solids, how much time do they have with the microbes to give the microbes a chance to digest them. So if you only have a few hours or minutes, they don't have enough time to do much to it. But if you have days or months in a lagoon digester, then the microbes have enough time to break that down into biogas. So let's talk a little bit about manure handling. So in the swine business, the animals typically live on a concrete slotted floor, and so the manure and urine and feces all fall through the slots into a manure handling system below the animals. And that can look like a scraper, which was a scraper system is one type where it's a shallow pit underneath the barn that has scrapers kind of depicted down here in the left-hand corner that push the manure to one end of the barn, and it goes into a sewer line and ends up into the lagoon. There's a couple other types of pit pull plug, and that's where it's more like your toilet at home, where you have a shallow pit underneath the animals that's filled with recycled water or fresh water. And that's sort of like the water in toilet bowl. And then it sits there for maybe a week, and then the farm operator will go out once a week and pull the plug and essentially flush all the liquid underneath that particular barn into the lagoon. He'll put the plug back in, and then he'll refill it with either recycled water or fresh water to a certain level, and the whole cycle starts again. There's also the flush system, which sorry about this picture, it was not a very good one, but there are some tanks that can sit outside a barn that fill, and it's usually about 800 gallons, and they might dump anywhere from 4 to 8 times a day, and they kind of create a tidal wave flush underneath the animals that push the manure to one end of the barn and into the lagoon. And that usually uses recycled water, or it can be used fresh water as well. And then for the folks in northern climes, there's a lot more deep pit in those, I guess, areas of the country, just because land is more valuable, and you don't get the solar input that you need to do like a lagoon digestion. It takes a much bigger lagoon to do the same amount of digestion in the northern climate. So, and then the deep pit, it's like an 8 or 10 foot pit underneath the animals, and the manure is stored for a period of 3 to 6 months, and land applied after usually outside of the crop season. So when I think about swine manure and how it gets into the lagoon and what's valuable about the manure, so as it comes out of the animal, it's somewhere in that 8 to 10% total solids. The rest of it is water. And then that gets diluted even further by what we call wastage, which is water that's coming out of, I guess, irrigation, or not irrigation, but like drinking water that's spilled, or any water they're putting in with the food that gets spilled, and are washing down the barns. And that might cut that in half from the 8% down to a 4%. And then if you have flush water or pit recharge water, that dilutes it even further because that water is coming from the lagoon or from a well that contains very little total solids, and you're diluting your manure down to that 0.5 to 1% total solids. So you have a very thin and dilute stream of waste coming out of your barns. And the total solids is typically made up of about 85% of what they call volatile solids, and that the volatile solids are the organic material that could be digested. Not that all volatile solids are digestible, but there is a portion of them that are. And I sort of separate those into three categories. There's soluble volatile solids, which are like the candy and carbohydrates to you or I. They're the easy things to digest. They're the things the microbes will digest first and fast. And then there's some suspended volatile solids, and these are colloidal type volatile solids that are floating in the liquid stream. They don't settle, they don't dissolve, but they are part of the liquid stream, and those are more the larger molecules than, say, the glucose or some of the smaller, more soluble. And then lastly is a settable volatile, which to me would be like broccoli, the stuff that's less edible by the microbes, but it has a much longer time in the digester, right? So if it settles to the bottom of the digester, it's there a long time. It may never come out. So it might have a really long time to sit there for the bugs to chew on. But at some point, the microbes don't eat it because they have all these other things they can eat. And then when we start developing a site, we want to know the manure handling and like how we're storing the manure. And there's three main categories. You can have an open lagoon, like this is depicted here, where the manure is coming out of the barn, going to an open lagoon. And then some sites have concrete vats where they're storing in a man-made lagoon, basically, or a more constructed lagoon than just earthen. And then the deep pits, which I mentioned before. I do want to stress that even though they're open today, like there's no cover on them, they are still anaerobically digesting the manure. And so your open lagoon is creating methane and CO2 today, even if you don't have a cover on it. And then when we look at a project, we like to have the open lagoons already available because potentially we could just throw a cover on it and it lowers our CapEx rather than building a new lagoon. And then the other benefit of having a lagoon is they have what's I have highlighted here, the GREET baseline. And for those of you who aren't familiar with GREET, it's a carbon intensity score that's used by the California LCFS market to score how much carbon is taken out of the atmosphere by what we're doing, right? And with a lagoon, you have a great baseline, and so you end up having a very low CI score, which is what you want, and you get more dollars per decatherm when you sell it in the credit market. On the converse, when we talk about deep pits, they don't have a very good baseline, and so they don't get the very good score, and so it's very difficult to get those California credits for a deep pit. So in our portfolio, we don't have any deep pit farms. And it's for that reason, because the economics haven't worked out just yet. It doesn't mean we aren't looking at it. We have it on our list to do, and we know there's a ton in the state of Iowa and other states that are out there, and we will tackle them. But right now, the economics just aren't proving to be in the right spot for us. So another aspect of the manure handling is land application. So depending on where you're in the country, you might have different ways of getting rid of the liquid in the lagoon. And in the Midwest, it's a lot of drag lines because it's done seasonally, either before planting or after harvest. In other parts of the country, they have irrigation pivots, and they're taking the manure right to a pivot, and they might be irrigating it year round, say in North Carolina. And then other sites that are maybe in I'll say the western climes that are much drier, they don't even land apply it. It's all evaporation. So they're building lagoons that have a lot of surface area. So they're getting plenty of evaporative capacity, and they don't have much rainfall, so they're just allowing all the liquid to evaporate and turn into what's left over is just the solids in the lagoon, and it builds up over, many 10, 20 years. So let's switch a little bit to temperature profile. And so when we're looking at a site, we'll find out, where it is, if it's in Iowa or Nebraska or wherever, and we're gonna, get the local ambient temperature, and that's this dotted line here. So that's what you can get off the websites from the National Weather Service or whatever. And then the line that's above it is, we have some temperature data from the lagoons that we've built in northern Missouri over the past few years. And this is the actual liquid temperature of that lagoon. And you can see it's not exactly the same shape as the ambient air temperature. And in this case, you can see like July would be the peak ambient air temperature. But for the lagoon, it's actually the water temperature is actually probably peaks in August. So there's that shift in when is the peak temperature, and that kind of dictates when your peak gas production will be. And so we are, generating shapes of the lagoon liquid temperature to try to understand how that's going to impact our gas production. So you can see in this chart down here in the left-hand corner, these are a depiction of like 4 year or 5 years actually of gas production. So the red and yellow is actual biogas production that we've had the previous 4 years at this site. And then the blue line is what we are modeling, how we're predicting based on ambient temperature, HRT, animal population. And you can see that, with our assumptions and the tools that we have, we have some offsets. I can see here there's an offset, but in general, it's matching the actual production fairly well. And so we can size our equipment based on some past experience. And so we're using this data from other similar sites to apply to new sites. And then the final big topic was like lagoon HRT. And the HRT, hydraulic residence time, is an easy equation. It's your lagoon volume. So how many million gallons do you have in your lagoon divided by what's coming out of your barn? And we determine that by how many animals are in the barn, what type of animals. So that gives us a manure rate, how many gallons per day. We would estimate a wastage number to add to that. And then depending on if you have flush water or pit recharge water or just a scraper, that might add some additional water coming out of the barn. And as that flows through the lagoon, it's only got so much time. So this is the gallons divided by gallons per day. You end up with HRT is measured in days typically. So the other thing I guess I wanted to mention is that we would want to avoid short circuiting. And so if I go back maybe, to like this lagoon picture for a second, if the sewer was coming in this corner from the barns was coming in this corner, we would not want to place our liquid removal system here, because then the flow of liquid would just be across this corner. You don't get to use the full HRT or the full volume of the lagoon. We would want to place it on the exact opposite corner so that the manure has to flow all the way across the lagoon, so you use all of the volume. So that's what I mean by short circuiting. So we would look at those sorts of things as well when we place our equipment on site to move the manure. Let me go back to where it was. I guess, some of the other things that we consider when we're designing the size of the lagoon is how long is the winter at a particular site, right? So some northern areas have, I'll say 4 to 6 months of like winter, and you want to store your manure for that period of time without letting it out of the digester. Because you can think about it, even though your animals are making manure in December and January, you may not be making any gas in those months, but you're storing that feedstock inside the lagoon digester that entire time. And then when it does warm up in late April and May, then you're getting to digest that stuff you've stored. And so you don't really lose it, you just produce it at a different part of the year. And that's leads me into kind of a discussion between why a lagoon digester versus a tank digester. And excuse me. So a lagoon digester, much less expensive. You're paying for a cover. If you've already got a lagoon there, we're putting a plastic HDPE cover over the top with some ballast piping. You can sort of see a picture here. We'll put some weighted piping on top to help it inflate properly. And then with a tank digester, you've got much more cost. You've got foundation, you got a solid tank, you've got a heating system and a mixers. So there's a much more capital investment to do a tank digester. On the flip side, a tank digester is heated, so it doesn't need as much HRT because it's hotter. It's running at 95 or 100 degrees temperature year round, and the bugs are more active at a higher temperature. So they're chewing up the volatile solids faster and making biogas, year round. Whereas in a lagoon digester, we have this seasonal cyclic, where in the wintertime it might go dormant because it's too cold for the microbes, but you're storing the manure again. And then when it gets to be June or July, you're making 2 or 3 times the amount of biogas you would make on average. So in our opinion, the lagoon digester is better suited for dilute streams. When we're talking about 0.5 to 1% total solids, that's a very dilute stream. So you need a lot of volume to get a good HRT. Now, a lagoon digester, because it's at a lower temperature than a tank digester, it operates it needs more HRT to do the same amount of digestion. So, and it's a little different depending on what part of the country you are, but let's say if a tank digester needs 30 days to do the digestion, we might need 120 days of HRT and a lagoon digester to do the same amount of digestion. So it's more volume to get the same level of digestion in a lagoon digester. Some of the other benefits of a lagoon digester is that it provides biogas storage. So if the upgrader or the pipeline closes you in for being off spec, then you have a few days to get that corrected, and you can just store the biogas and produce it the next day, take it off the lagoon. Whereas a tank digester has very little gas storage. In a matter of minutes or hours, you're full and you have to start flaring it. So you actually lose the gas. And a lot of our sites, we don't even put flares in because we have this surge capacity. So if we go off spec in the pipeline for some reason, we just recycle it back to the lagoon and we'll process it, the next day or the day after. And we don't lose that gas. Even though it wasn't on spec, we'll make it on spec the next day. One of the downsides of a lagoon digester is that it's cyclic. And so you have this peak in June or July. And let me go back to that slide, maybe. So you have this peak here in the middle of, it's usually in June or July in the Midwest. And so you have to design the capacity of your biogas upgrader to meet that peak. Whereas if you had a tank digester, it's going to be a continuous gas year round, and it might be a capacity of maybe 2 times less than what the capacity is needed for a lagoon digester. So you save some money on building a lagoon digester, but you're going to spend more money on your upgrader because you got to make it bigger. And then the last thing I'll mention is just related to this carbon intensity score. If you have a lagoon digester, you're not adding heat, so very little parasitic load. And what we've seen is in those cases, we get very good CI scores, -300 to -400 carbon intensity. And that gets you more dollars per MMBTU from a credit standpoint. Whereas a tank digester, you're adding energy for mixing, you're adding energy to keep it hot. And then you also might overproduce compared to this baseline that I mentioned, which will also hurt your CI score. And so you actually have a less negative, or you might have a negative 200 or 250 score in a tank digester. So, just moving on and trying to summarize on how we approach projects. One of our first questions is, does a lagoon exist? And this really goes to the credit generation and being able to be a participant in the California LCFS program. Because when you have a lagoon, you have when you have a lagoon, you're going to get a better CI score, and you can sell that in the California market. Then we'll ask, some very high-level questions about your animal population and animal type, so that we know how much manure we could expect from these barns, and that translates into how much gas we would expect. We have we'll ask you about your manure handling, scrapers versus a flush system or a pit pole, because we have some discounts that we would provide. Like scrapers are providing very fresh manure every day to the digester, whereas a pit pole is only providing fresh manure once a week, right? It's not, so you're losing some of that volatile solids while it sits there for a week underneath the animals before the plug is pulled. So we want to know how that things are being handled, so we can get a better estimate of how much gas would be produced. We'll look at the temperature profile, and so that helps us determine the size of the biogas upgrader. And then we'll look at like HRT, like how big are your lagoons versus, how much manure is coming out of the barns, and does that HRT meet the minimum that we would need, let's say, to digest, or we can, discount it and say, well, you don't have enough volume there for the amount of digestion we would like to do. So instead of making 90% of the gas, it might only make 80%. Or you may have so much HRT that it doesn't even matter. And we've seen that in a lot of our sites in northern Missouri. They were designed for open lagoon with a lot of rainwater. And so they're oversized and have HRTs on the order of 300 to 400 days. So they're actually able to store their manure for over a year in most cases. But other sites that we have, they're more on the order of, say, 120 days to 160 days. The other couple of things that are kind of outside, let's say, the farm owner's control or anything, is like the pipeline tariff. So if we have a site that has multiple lagoons like this site, this is in southern Iowa, and we've covered 5 different barn sites and aggregated them into a single upgrader, which is actually located right here in this little spot here. We aggregated those, and then we're actually trucking this, so that would be another decision. Is it easier to pipe this renewable natural gas to a utility natural gas pipeline? Like if there was one a mile away, it might be easier to do that, pay for the interconnect, than it is to put in the system to load it onto compressed natural gas trucks, drive those trucks to another location that has an interconnect, and offload them. In this case, we actually are doing that. We're driving the trucks to a site in northern Missouri, and we're offloading those CNG trailers into a pipeline interconnect that we already own and operate. We would also contact the local utilities for electrical, and if we needed any buyback natural gas. So we want to know what their capacity is, and can they handle the equipment it takes to do the upgrading. So we would give them an estimate of how much power we think we would consume, and then could their system handle it, and are there upgrades needed to supply that power? Then we would get into a capital estimate based on the projects that we've done. And we've done, I would say up over 60 projects now. So we have a pretty good database to pull from on what things cost. And similar projects, we would, use that in our estimate, come up with a CapEx estimate. And then we would do the GREET model to figure out what our CI score is, understand what programs we would want to be part of. And I've got a slide next for that. And then determine the overall profitability of the project. What's the payback? Is it a 2-year payback or a 7-year payback? And just kind of lay that out for us and the farm operator for partnering someone who's ever investing. So to talk a little bit about credits and the different programs. So you can think about the gray gas as the actual molecule, like fossil fuel natural gas. It's really equivalent on a BTU basis that goes into the pipeline. And so, as we put RNG into the pipeline, there's this gray gas component that is treated just like fossil fuel, and you get $2 to $5 per MMBTU. Then there are 2 main programs that we are involved in. There's a federal program called RFS, and our manure renewable natural gas qualifies for D3 RIN, and it can typically be worth about $15 to $30 per MMBTU. And there's a new program that's similar to that being started in Canada, and we think that's going to be maybe a little bit better. It's just a little early to say. I think they're just starting that up now, and they haven't defined all the regulations just yet. And then there are state programs in California, Oregon, Washington, New Mexico, and that is on top of all these things, right? So you can see this chart here. You get $2 to $5 for the gray gas. You might get so much for the RFS federal program. And then on top of that, you'll get a state program if you participate. And in all these cases, at least in the credit programs, it's not about the molecule getting to a particular state. It's about the data that supports that to prove that you have produced it from, let's say, swine manure, that you've used so much energy to make it into RNG, and those decatherms were actually injected into the pipeline. So all the data around all that to be a participant in the program is very important and critical to getting those kinds of prices for the renewable natural gas that we're putting in the pipeline. And then if you don't qualify for some of those programs, you might look at a voluntary program. MRETS is one that's in the Midwest, and then there's ISCC, which is international. And this allows you to work like one-on-one with a company that's trying to reduce their carbon footprint, say a Walmart or an Amazon or Google or someone that's trying to reduce their footprint. You could, negotiate a deal with them to sell it through the MRETS program or the ISCC program, and get a price if it didn't qualify, or maybe you can get a better price through the voluntary program than you can from a state or federal program. So those are all decisions that are kind of made as we're developing the projects to try to understand what outlets we might have for the RNG. And then some high-level numbers of like what does it cost to build one of these sites. For a lagoon digester, we think of it in a CapEx dollars, like somewhere in the order of $80 to $100 per million BTUs of RNG injected is what a lagoon digester would typically cost. And it can probably cost less if you already have a earthen lagoon sitting there and all we have to do is cover it. But if you had to build a new earthen lagoon, that would be that 80 to 100. And a tank digester, just for comparison, is on that order of $200 to $250 per MMBTU to produce the same amount of gas, essentially. And then you have the upgrader, which is another $80 to $100 per MMBTU, and the total cost, which includes interconnecting piping and some auxiliary systems, would be on the order of like less than $250 per million BTUs of RNG injected. And this, I put in this little caveat that excludes the pipeline interconnect. And we've seen pipeline interconnects cost anywhere from like a $500,000 up to $5 million. It really depends on the pipeline you're dealing with, what pressure it's at, and if they've done it before. Um, so if they've interconnected with renewable natural gas before. So uh, it's a very wide range. Sometimes you can actually get the cost of the interconnect included in your OpEx. So there's some ways to defer that CapEx. Right. And then lastly, I just wanted to share sort of, again, we have a wide portfolio of membrane upgraders that were developed in-house, anywhere from 25 standard cubic feet per minute of biogas up to 400 scuff a minute on this platform. And then we have other bigger compressors and membrane skids that go all the way up to 1,800 scuff a minute. And then we've got PSAs that we own and operate up to 2,200 scuff a minute. So, we can fit the right size upgrader to your size facility. And that's all I had. So are there questions?
We do have one question, and then I have a few
Oh,
more for you as we go. So the
okay.
first question is from Luke, and he asked, how does the HRT vary at swine-covered lagoon sites? And I know you talked about that some, and it's very temperature dependent of the place you locate it.
Yeah, so and I wish I probably neglected to put a curve in here, but as you can maybe imagine that there's a curve called the biomethane potential curve, which is on the x-axis, it's like days, 0 to 30 days or 0 to 100 days. And then on the y-axis is essentially how much methane are you producing as time goes on, right? And so it's not a straight curve. It's a logarithmic curve that has a knee in it. And for a tank digester, you get past the knee, and so there's no need to increase your HRT past the knee because you spend a lot of money and you don't get much benefit. But on a lagoon digester, that knee in the curve is less pronounced. And so you need more residence time to get the same amount of digestion. It takes longer. So that's why we get to that 120 days of residence time versus a tank digester. So 4 times more residence time. And it depends on where you are in the country and its temperature profile. So it is temperature dependent. And we develop a curve based on the temperature profile. So
Perfect. And in December, we're going to talk a whole bunch about BMP curves and how to
okay.
interpret them and how to make the most of it. So that was a great lead in for that. So if you want to learn more, show up in December. Brad asked the question. He said you did a great job. And then you
Yeah.
mentioned some projects in Iowa. I think of you as a Missouri company moving north. So his question is going
Yeah.
to gear into that. He's from Minnesota, and he'd like you to tell him maybe some of the challenges as you try and keep moving north. And he gives you a few things to pick from. Is there a major
Yeah,
challenge?
I
Deep
we
pits, winter,
so
etc.
yeah, we've done a project in southern Iowa, and we have actually two lagoon digesters in southern Wisconsin, so not quite to Minnesota yet. But I would think the main concerns are temperature profile. The winters there are much longer, so then you would have a much shorter, I'll say, active season for the microbes. It might not start until middle or end of May, and then it's going to get colder sooner. And so you've got a shorter window to actually consume all those volatiles and make your biogas. And that leads to, needing a larger lagoon. So you hold all your manure longer to get it through that cold period. Because if you don't hold it during the cold time and it passes through the digester, you lose it, right? And so if it leaves your digester before it gets warm enough to get digested, well, that was your shot. You've lost that feedstock. And so it just means you would need to have larger lagoons to do the same amount of biogas production in the northern climate. And that leads to more cost, right? So that's where it's tougher as you go further and further north. The cost, that $80 to $100 per MMBTU, continues to increase as you go further north.
Yeah, and you mentioned a little bit about how lagoons can be an advantage. You settle some of those volatile solids, but you still eventually have to get it to convert, and that's sort of the
Right,
challenge as you move north.
right. And then there's other, like, I'll say, smaller costs that a lot of our upgrading equipment is not, I'll say, winterized for the severe winters that you probably see in Minnesota. So we might have to upgrade insulation or heat tracing on some of the equipment to, you know, make it operable in colder weather.
That was one of the questions I was going to ask you. How do you winterize? What does a winterization of your especially cleaning equipment look like?
You know, a lot of our stuff, it sits outside. We don't have it inside buildings. We are knocking out water as part of the upgrading system. So anything that's condensing water, we'll have it insulated and heat traced. We have a few, like the membranes, need to be temperature controlled. So they're usually in a container that has a heater in it. And then there are certain parts of the process that we're insulating to maintain heat that we've created from, let's say, waste heat from the compressor.
Mhm.
So
Perfect. And then we have a question on how is lagoon monitored for erosion of the liner inside the cover or just condition of the lagoon once you've put a cover on? And sort of in that realm, could you maybe talk about how manure removal has changed at some of these farms after they've covered it compared to before?
yeah, so you know the HDP cover, and we use typically like 80 mil HDPE, and so it lasts a very long time. We've got lagoons that have been covered since 2013, so 12 years, and we haven't replaced them, right? So the covers last for a very long time. I will say that there is some annual maintenance that has to be done on a cover because they do, you know, flying debris from storms. Animals can get on there and, you know, their hooves might poke a hole in it. If it's a deer or a loose cow or something, um, we've had that happen. But really, the covers are pretty tough. In fact, when they install them, they use like ATV four-wheelers and they drive on them, right? So it's not like they're thin and easily punctured, but you know, a windstorm with flying sheet metal can cut a hole. Sometimes the ballast piping can rub and cause holes into the cover. And so in the off season, we do some exercises with the team and go look for leaks, and then they're easily patched. So the next season you're not leaking that biogas and you get to capture it. So there's some manual or some annual maintenance that has to be done. And then as far as like solids build up over time, again, we're starting to see more of that, I think, in some of the older lagoons. Typically they're built with a lot of extra storage capacity because no one wants to remove the solids, even in an open lagoon very often, right? But the amount of solids is, you know, a function of the volume of the lagoon. And we have lagoons that have been in service for 10 years that we have not had to go in and clean out. You know, we've had to do a few things where you can imagine at the end of the sewer line entering the lagoon is where the settleable solids fall out. And so you have this big pile that builds up over time. And we've gone in and used a high flow rate like pump to kind of blow that pile up and push it away from the end of the pipe to get us more time. And we've been able to do that pretty routinely without having to like peel back the cover and actually get in there with equipment to remove the solids or sludge. And
Perfect.
typically when we start a project, I'll just mention, you know, if there's a lagoon that's been there for 20 years and full of sludge, we want to know those sorts of things. We'll do a sludge survey and before we put a cover on, we'll come in and, you know, if we need the HRT, we'll say, well, we need to get rid of, you know, 10 million gallons of sludge before we put a cover on because we don't want to go in there after the cover's on. It's just more difficult.
Perfect. Thanks, Eric. We're getting all sorts of questions. Do you ever see any covered lagoons where the influent is preheated?
Um, I guess in a little bit, we have these dairy digesters in southern Wisconsin where they're using a flush system and they're like totally enclosed in a barn. The animals are in a barn the entire time. So the manure's in a barn and that barn is temperature controlled. So, you know, it just happens. It's not purposefully heated, but it is heated because the animals are in a heated barn. And so even in the winter, we're seeing manure coming to our lagoons that's in that 65 or 75 degree temperature, but outside it's 20 or, you know, negative 20. You know, so in a way it's heated and we do see gas. We've actually produced gas in southern Wisconsin in January and in February, right? So it's not like it goes completely dead because you have a little bit of warm manure coming in the lagoon. And of course, it's reduced, right? We're not making our peak production, but we are making some gas. And so, what we are able to do is it's not like you're running your equipment every day. You might shut down for a week, let the gas build up under the cover, and then you run for 3 days, pull all your gas down till so there's none on the cover, and then you wait another week. And you just kind of do that throughout the winter, just because production is lower than you really need it, you really want it to be. So
And then Brock asked a follow-up question. Would preheating be economical, or would that be counter to the cost savings uh, of a covered lagoon?
I mean, in a way, it depends, right? So as you can imagine, that peak in the curve, if you can get more of the volatiles digested in the colder shoulder months, then that peak is shallower, right? So you don't have to make your upgrading equipment quite as big if you could heat the lagoon. Now, when we talk about lagoons, they're not small, right? These are lagoons that are probably containing anywhere from 15 million gallons to we've got some as big as like 40 million gallons. And so you can imagine heating that many gallons of liquid, and then it's losing energy to the earth, right? Through just natural convection to the soil, because the soil's at 45 degrees. And then it's losing some off the cover because it's wind, convection heat, but it's gaining some from the solar. So, but at night, it's not gaining anything. And so there's that heat balance that, in our opinion, when you look at that, it doesn't make a whole lot of sense to try to heat that large of a volume. Because remember, you're very, very dilute stream at less than 1% total solids. So you're heating water, but you're not getting any value from heating water. You want to heat the solids.
That's a great answer. And maybe I have a student, Luke, who's been working on some heating costs and sort of what it would take to heat these systems. And it echoes a lot of what you've said there. And maybe we'll see if we can twist his arm to give us a presentation on that. I'd also say,
Okay.
Brock, a colleague of mine, Raj Raman, back who was at the University of Tennessee, did sort of what you're asking about. He put what I'm going to call a parasitic digester on a lagoon, and he would cycle material through that heated digester that was relatively small and use the lagoon, mostly trying to convert volatile fatty acids that he made in it. So there's some work out there, and that might be a place to
Yeah,
look.
and we have two sites that are similar to that, where we have uh, the Horizon 2 site, Dan, which you're
Hmm.
familiar with, where we have two tank digesters that are heated to 100 degrees, and then the effluent, the output of that, actually goes into a lagoon digester. So all that hot liquid is coming in to heat up that lagoon. And so, that's helping that lagoon perform better. We can make it smaller, less residence time because it's getting, 100-degree material coming in one end. But when it leaves the other end, it's not 100 degrees, right? It might be 80 degrees. So, that's in a startup mode right now. So we don't have a whole lot of actual data yet to, prove that theory or whatever. And then we have a site in New Mexico that's very similar where they have tank hydrolyzers, which is a very short residence time. So maybe 2 to 5 days of residence time just to make some volatile fatty acids. And then that dumps into a lagoon digester, which is heated and mixed. So that in that particular site, we are mixing it. And then we are also, we have like heat loops that are heating the lagoon. And so we're making gas, but we're not making as much as we'd like. And it's more of at that site is particular, it's a feedstock issue. So.
Perfect. So there's lots of opportunity out there, but still lots of unknown. And then I have
Sure.
one final question for you, and it's really related to your evolution of gas cleaning technologies. You've done some pressure swing, you've done some amine, you use a lot of membranes right now. Could you just talk a little bit about the progression of that and how it is helping us think about scaling to smaller farms?
Yeah, I think the pressure swing absorption and the membranes are very similar. Not so much in technology, but just in how much power they use. Uh, we find that the PSA is a little bit more sensitive to starting and stopping. It takes longer to get it up and on spec than a membrane system does. It's more hands-on for the operator to, when they are changing the flow rate or changing how they want to operate, it's a more manual, I'll say, adjustment, where the membranes, You set them and pretty much forget them. So it's a much easier uh, day-to-day operation. And then the amine system, what we've seen so far, it's just at a smaller scale. It's just not economical, but at larger scales, like above 1,500 to, I don't know, 5,000 scuff a minute, the amine systems are much more economical. And, that's probably where we'll head as we get into, there's some sites we're looking at, not manure sites, but other feedstocks that might warrant themselves to have an amine system versus a membrane. Because a membrane, you are using a compressor to compress it from, say, 0 pounds atmospheric pressure up to, say, 200 pounds of discharge pressure. And we have some compressors that are 600 horsepower, and we might have 2 of them on site. Well, and that's for an 1,800 scuff a minute unit. But if you're talking 3,000, okay, we might have 4 or 5 of those in parallel. So that's a lot of horsepower to energize from the local utilities. And a lot of times these are very rural and remote areas. So the utility systems aren't designed to handle that high of electric load. And so it's, you have to make some of those decisions. And that's one of the things that happened to us in Texas. And when we did the amine system was that the local electric system couldn't handle the compressors that we were first, I guess, proposing. And so that's one of the reasons we went to a amine system, because they use a lot less electrical, but they use natural gas to regenerate the amine. The overall energy consumption is about the same as a membrane system, so it doesn't really help or hurt your CI score. They're very similar, but it just changes your parasitic load, who you need to talk to, or what the capacities need to be. So.
Perfect. I think, first of all, thank you for sharing so much of your experience and how you've been putting these projects together. I think it was a great presentation today, and I really appreciated it.
Oh, thanks.
A few notes. Next time, we'll meet on August 12th, and Robert Burns from the University of Tennessee is going to talk about the Deep Pit Barn Challenge and how manure removal frequency impacts methane production, and then options for improved removal, which Eric pointed out to us is really important and one of the things they think about for these projects. Let's see, what else am I supposed to say? We do post these on our YouTube channel, so youtube.com/Dr. Manure. We'll get it posted hopefully within a week for you all to enjoy. So if you want to watch past webinars, they are there. And we do have a newsletter for anaerobic digestion that is quarterly. So if you are interested in that and getting a summary of these presentations, I've put a link in the chat that you can use. So once again, thanks, Eric. It was great to have you here today.
All right. Thanks very much.